Bismillah ar-Rahman ar-Rahim. We will continue with Boolean Algebra chapter. So you need to watch first the two previous videos covering the basic simplification theorems in Boolean Algebra. Now I will continue with new theorems, more theorems. So make sure that you understood whatever is in the two videos before in order to be able to follow with me here. So, simplification theorems that we will cover in this video are the three given here in this slide. So what you have here in this slide, you have three theorems, and for the three theorems you have three more theorems here that are related. How they are related? The theorem here at the right side of the slide is the dual of the theorem at the left side of the slide. So the first theorem, x ended with y, or x or xy prime equal x, has dual x plus y ended x plus y prime equal x. So what is happening here? The three theorems at the right side are the dual of the three theorems at the left side. So let's see what means this. Okay, I will start with the first. So I said the first theorem that I will explain here, it has dual the theorem at the right side here. So how we can find easily the dual? Just we need to replace AND operation by OR operation, and the OR operation we need to replace it by AND operation, and we will get the dual of the expression. So I have x ended with y, or x ended with y complement is equal to x. How we can get the dual? So here I have AND operation. I have this term ORed with this term. So between the two terms I have OR operation. And in the first term here I have x ANDed y. So x ANDed y will be x or y. This is the first thing. And this OR operation will be AND. Okay? And this AND operation here will be, and this AND operation here that you have here will be x or y prime, or y complement is equal to x. And in this way, we are getting the dual. Clear? So now what I need to do, I need to prove these two theorems and to show why they are valid. So let's prove the first part of the theorem. The proof is very easy, but you need to remember all your basic theorems. You need to remember them in order to use them to prove whatever is here. So I have x ANDed y, or x ANDed y complement is equal to what? I need to show that is equal to x. What we can do here, very easy, we can just take x common factor. It will be y or y prime, right? Is equal to what? So you need to remember y or y prime is equal to what? Y or y prime is always equal to 1. So I have here x ANDed 1, which is equal to 1. And this is the first part proved. What about second part? In the second part, I have x or y ANDed with x or y prime that we need to show it's equal to x. So let's develop the expression to open the parentheses to see what is giving this. So very easy. When we open the parentheses, as we do in algebra, the normal algebra, the ordinary algebra, we have just to multiply out. It's equal to what? So I will x with x, x with y prime. So it is equal to x ANDed x, or x ANDed y prime, or y ANDed x, or y ANDed y prime. So what is giving this? This is very interesting. Why? because I have already x ended x is equal to x. Any variable ended with itself, it's giving the same variable. Any variable ended with its complement, it's giving what? It's giving 0. So the remaining terms are x, y prime, or y, x, or 0. This is equal to what? Something very interesting here, that I have x common term between the three terms. So I will take it out, common factor x, it will be 1 or y prime or y is equal to what? 1 ORed with anything is equal to 1. Okay, don't forget this. 1 ORed with anything is equal to 1. And even I have here y complement or y, it's giving 1 also. So anyway, I have 1 or 1 and ended with x, so this is equal to x. So you have the proof of this theorem of the two sides, the theorem and its dual. Let's continue with the next theorem. Also, this is the dual of my first part, where the or is replaced by and. So how to get the dual? I have or between this term and this term. So I will replace this or by and between x and the second term. The second term is x and y, so I will replace the and by or. This is equal to x, and this is my dual. Okay, now let's prove them. The proof here is very easy because my expression is simple. So I will just put x common factor 1 plus y. So this is equal to what? 1 plus y is equal to 1. X and 1 is equal to x. So done for the first part. Second part is also very simple. So I will multiply out x and x plus xy is equal to what? X and x is equal to x plus xy. So I get my first expression. Okay, I will continue in the same way and I will have x. So proved the second theorem. Let's move on to the last one. Last theorem for the simplification theorems. What we have here, this is a very interesting one. Why? Because you need to remember the distributive law. You remember the distributive law? What was the distributive law? I said when we have A or, for example, B and it's C, this is equal to what? It's equal to A or B. We distribute and did A or C. Remember this? So if you remember this, we can apply it to our theorem. So I have x or x complement ended y is equal to what? I will distribute. So the distribution will give me x or x complement ended with x or y, right? X or x complement, it's equal to what? It's equal to 1. 1 and this expression, it's giving x or y, so this part is proved. Let's go to the dual. The dual, what is giving? So this is, the dual is giving something, it's something very easy to prove. Why? Because I will just develop plus xy is equal to what? X ended with x complement is equal to what? Yes, it's equal to 0. So x or y is equal x to x ended with y. Good. So you need to memorize the 3 simplification theorems in order to use them to simplify very big expression in Boolean algebra. It's very easy. You have to master your theorems, and in this way you will be able to use them. Last thing important in this slide is De Morgan's law. This law is something very beautiful in Boolean algebra. Why? Because it will enable you to simplify operations that are under the complement operation. So if you have the inversion of or the inversion of and, or the inversion of big expression, this can be simplified by using De Morgan's law. So what states this law? We have two things. First, if I have a NOR operation, you remember what is a NOR? NOR operation is performed by NOR logic gate, صح? So if I have here X and Y, I have here at the output, it's not nice, my NOR. So what I will have here at the output, I will have X or Y inverted, صح? Inverted, you can use this, or you can use just prime as in your textbook. So X or Y inverted, it is equal to what? According to De Morgan, this is equal to X inverted and Y inverted. So what is happening here? The or if you want, the NOR operation is converted to AND. So be careful. If I have a NOR operation, this is equivalent to AND operation. But what? But my inputs are inverted first. My inputs are inverted, and I will have this X complement and Y complement. This is equivalent to NOR operation. So this is what states De Morgan. De Morgan states that if I have NOR operation is converted to AND operation. But don't forget, we have first to invert the inputs. The inputs are inverted, then ANDed together. Right? So, okay, this is the first part of De Morgan law. Similarly, we have this is applied for the NAND operation. شو معناتها? This means if I have AND operation here, sorry, NAND operation, NAND, X, Y are ANDed مع بعض and NANDed مع بعض, NANDed together. So what is happening? This is equivalent to if I have OR operation, but what? But don't forget first to invert the inputs. So if my inputs are inverted, if I have here X and have Y, so at the output what I will have X complement or Y complement. This is equivalent to this. This is very important. Why? Because when you have an expression under the complement operation, you can open this, you can break this by using the NAND will be NOR, the NOR will be NAND, and we don't have to invert the operation. Anyway, this you can use the benefit of this when we solve simplification examples, okay? So you have to review all your simplification theorems very well, that I can solve simplification problems in the next virtual lecture. Okay, so review very well, prepare your question, and be ready in the virtual class, be ready because we will solve examples, more examples.